Thank you for coming to the talk, and I'd like to thank the organizers for inviting me. Over lunch, we had a heated discussion of what is deep learning, so maybe I'll spend quite a bit more time on that. There's also something else I do called reinforcement learning that people like David Rios in the back and a whole bunch of other people around here have, I think Fabrizio might have done, no, maybe not. So there's two ideas, deep learning and reinforcement learning. I also have like 3 applications, but I'm not so sure that I'll be able to do all 3. One is I wanted to try and explain how Google has an algorithm called AlphaGo. That was one out. I've got another application on finance and another application on these things called agent-based models. But given the time, I don't think I'll be able to. Maybe I'll pick one of the 3 and see what happens there. But my big goal is to try and reduce some of the stress about deep learning and try and sort of explain what the opportunities are for deep learning. So where do I come from these types of things? So I come from the Bayesian decision world, utility maximization under uncertainty, things that we used to do a lot. An area turned up in computer science called reinforcement learning. That's just the computer science jargon for solving these Bellman optimality problems that are in economics and finance. Actually, I think this idea here is interesting. So when I get to talk about the AlphaGo, the computer science people will call this imitation learning. And to a stats guy, it's a very simple idea, right? I'm just going to take a huge big data set. So for example, this algorithm AlphaGo played a famous board game called Go with the black and white counters. It also learned how to play chess. I know David likes to play his niece at chess. We had that this morning. Well, what do they do with imitation learning? They took 23 million games of chess players, of famous chess players, and tried to build a model of what would the next best move be for these chess players. So there was really no model to begin with. It was just a huge data set, right? And then the rather interesting thing is, once I've quote unquote learned from my 23 million chess players what a good move is, I can let the computer play itself, right? So I can't remember who was the guy that wrote the book about 10,000 hours, was it Malcolm Gladwell? That if a human spends 10,000 hours to be good at something, well, just imagine a computer, right? It can play chess against itself 10 billion times, and it can lose the first 9 billion, and then it can start to win, right? So in this imitation learning approach, they would start by training on human data sets. And then they'd realize that humans were not really very good at playing chess, and humans are not really very good at playing Go, right? And they'd just let the computer play itself, and the deep learning algorithm would learn a better and better strategy, right? Or policy function, as you would say, right? The value function would be just trying to maximize the probability of winning at Go or winning at chess, right? So I see this area as something that is coming to a lot of areas, right? Not just board games like chess and Go, but even things like healthcare. So Google has a company called Google Verily that's collecting big data sets on images of cancers. Take 1 million people who have had a certain cancer, do some deep learning, pattern matching, and trying to figure out what would be cancerous or not. So healthcare is a big area. And right? Every time you pick up your phone, right? Gmail uses deep learning. Google Assistant, if you have one of those horrid OK Google, switch off the lights kind of thing at home, right? Amazon Alexa, face ... right? And I think if you look at Google, 5 years ago, there were no applications of deep learning at Google. They've got like 100,000 people work at Google now. So 5 years ago, they were close to 0, right? Now, if you look, there's 6,000 applications of deep learning at Google. So recommender systems are now all deep learning. Gmail is deep learning. Google Assistant is deep learning. Google Translate is deep learning, ... right? So I guess my idea is that at some stage, old problems that we used to like to do, and even old statistical problems that we like to do, will all become deep learning. So that's my. Maybe you guys can disagree. I'm sure Nalini will say, Nick, how can everything be deep learning, right? Okay, so I've got one math slide to try and explain what deep learning is, but I'll also talk about it more from a statistician's point of view too, right? So maybe let me start with. So I had to do something for Noza and something for Ernest, right? So here's my.
Why do you put us both in the same basket?
I don't think you ever met Kolmogorov, no.
I did.
You did?
I did. I did meet him, I had a drink with him, and I went to his house. But he was dead. When I went to his house, he was dead. But when I had a drink, he was alive.
He was alive. Oh, so you met him twice, right? Once dead and once alive.
But I see him in my dream every day.
You see, I'm building a data set. I want a data set of when did he see him alive, when did he see him dead, and alive I can predict knows his drinking.
Now,
Right?
I do have a picture when he was alive with a drink. But then I went to his house. Shreya have invited me. And so I saw his house. I saw a lot of things inside, and I can talk about that because it's quite interesting what he had in his house.
So what did he do for computer science, right? He essentially invented the method of deep learning. So let me just quickly say, what did Kolmogorov do, right? Actually, he was solving something called Hilbert's 13th problem.
Right.
One of the. So here's what Kolmogorov, and actually his student Arnold, but Kolmogorov's theorem, right? There are no multivariate functions, just superpositions of univariate ones.
Yep.
So it's in some sense, it's sort of an incredible result, right? So what do I mean by that in terms of math down here, right? You know, stats guys are always trying to find, you know, non-parametric regression. Some nonlinear function of my inputs to give me some prediction out here, right? Any stats model will hopefully end up with a prediction somewhere. I want a multivariate function. Well, what did Kolmogorov do for us? He says, oh, look, you know, it's an incredibly high-dimensional, complicated multivariate function. I can decompose it as a convolution or a superposition. So the little f, a univariate, right? So think of the simplest possible function, right? Like the maximum function. Maximum of x and 0 would be one of these. Or a linear function, right? Or the sigmoidal function, right? That's univariate. The computer science guys would call it an activation function. We used to call it a link function in stats. So that's univariate. And then there's just a regression in here, right? So in matrix form over here, but essentially just a regression, right? Oh, and I hate it when people call them neural networks. Well, why do they call them neural networks? Just a regression. N sub L is the number of nodes. No. N sub L is just the number of terms of my regression, right? So all it is just a sequence of univariate semi-affine functions that get composed on each other, right? So down here, essentially what do I do to my input variable x, right? It's just a sequence of filters, right? So maybe x is an image, right? I want to predict whether Noza is going to drink a beer or not, over here, right? I look at the image. Okay, that's 100% Noza, okay, fair enough. But I take an image, a picture, and I want to classify it as something. I just apply a sequence of filters to it. A regression, then a univariate function, and then replug it in, another regression, another univariate function, and compose up, right?
Just a matter of clarification. I think Kolmogorov proved it for the 3-variable case.
Yes.
Arnold proved a negative result and then generalized it to the multivariate. So
Yes, that's
can
true.
you clarify exactly the connection between the two? I mean, I think Kolmogorov proved it only for 3 variables. And the computer scientist who spoke this morning, very impressive talk, also had the 3-variable case there. So I'm wondering if there is a connection.
I don't think the 3 is related.
I think it is.
It's greater than 2, maybe that's the only, or less than 4, whatever.
I think there is some relation.
Actually, so let me just step back, right? You can actually get away with L equals 2, as long as you make the second function non-differentiable. So the first theorem that Kolmogorov proved was, you can actually get away with...
For 3. His first theorem was for 3.
Oh, for 3 x's, right? X1, x2, x3, right? But the initial theorem, right, which in the 1980s people call them neural networks, right? People just stuck L equals 2, and they just started to run these regressions on L equals 2. Well, the neural networks, as we remember, didn't work, right? Well, why didn't they work? Well, it's looking here, it's sort of obvious, right? They just stuck L equals 2. So the modern day versions of these things are, okay, let's just make L equal 5, let's make L equal 10, ... Now, you know, I've seen people go down to like L equals 150, right? They just keep on increasing L. And people have thought about, okay, how big should I pick L, right? Oh, one other thing I should say is, you know, why will this come to stats is There's a set of programs where there's two major competitors, something called TensorFlow that Google created, and something called PyTorch, if you like Python, PyTorch. Actually, one of my friends was one of the developers of PyTorch, so there was a battle between TensorFlow and PyTorch. Inside TensorFlow, you can run TensorFlow in R. So for all of you young people that like to use R, you can use a program called Keras. Keras will call TensorFlow, or you can use my friend, you can use Clement's PyTorch. The genius thing is, of course, it'll quote unquote estimate the weight matrix, and they're called offsets rather than intercepts. So TensorFlow will just compute all of your weights and offsets. It won't tell you what L is, and it won't tell you what functions to use, right? The univariate functions. But a typical network would just use the maximum function, maximum of x and 0. Oh, and one other thing that sort of annoys me about machine learning, given my old age, is they take everything we've done in stats and rename it. They even do the same thing with math, right? So the maximum of x and 0, I call the maximum function. My computer science friends call it the rectified linear unit, or the ReLU network. My Berkeley stats friends would call it the hinge function. So I'm just English. I'm not very good at these kinds of words. So I still call it the maximum function. Why does max work? In some sense, you're just doing a high-dimensional problem by finding separating hyperplanes, right? So if you think of the geometry of what it's doing, it's a separating hyperplane approach, right? Got a huge big data set, separating hyperplane. And you can see why that's better than trees, right? Trees are finding cylinder sets. So I know Bo this morning was entering. Now, gradient boosting is a great idea, right? So one other thing that I've learned from my computer science friends is you just need to know stochastic gradient descent, SGD, or to me, Newton's method. So remember everything's renamed, right?
Actually, Robbins Monroe.
Well, I think Newton was before. I didn't have a beer with Newton.
But the stochastic part was not in Newton. The stochastic part came in Robbins.
Are you sure, Noza?
I'm sure of nothing.
So I'm joking that,
But do neural nets use...
Well, we can't say neural nets. We have to say regression. That's a neural net, right, with N-sub-L nodes, right? So I'm sorry, I have my stats bias, right? Actually, all it is for the stats audience, right, we would call this a generalized linear model. Peter McCullough is a very good friend of mine that did generalized linear models. A generalized linear model with a link function that's a composite. A composition of filters, right? Now, and again, that's an important point, right? Where did the stats guys go wrong? They do additive models. So huge errors, I mean, just beyond me, right? Principal component regression, principal component analysis, principal projection pursuit regression. All of that work that Stanford and Berkeley did, that David knows a lot about, right? They made the big mistake of L equals 2, a linear combination of functions that's additive. And stats are we're still doing additive models, right? GAN models, generalized additive models, right? So the computer science guys, very smart, right? They took Kolmogorov's theorem essentially, pick L equals 10 and L equals 50, pick this to be the maximum function, run gradient boosting that Bo was talking about this morning, or stochastic gradient descent, estimate my weight matrices, and pattern match a data set to get my prediction. So I think that's a good way of thinking about deep learning. And another thing to remember is that this TensorFlow code, it's Google ready code, right? YouTube is running on TensorFlow.
So what is the F function? What is the F?
Yeah, these are just univariate functions.
What is L? What is L?
Oh, so L is the number of layers, right? So I'm just composing.
So what's multiplicative and what is that? All that is additive. The Kolmogorov function is additive.
This little piece here is a regression, additive.
Yeah, it's additive. So
apply it in a simple nonlinear function and then compose it, right? So that's the input of the next function, right? It's a sequence of filters, right?
So you said they did something nonlinear. What is it?
Well, this is nonlinear to begin with, right? This is linear, nonlinear.
F function is nonlinear?
Yeah. This is semi-affine, linear. This is a little nonlinear function. But most of the nonlinearity gets created by just, the argument of this one becomes the argument of the next one, right? It's a composition of functions, not an additive one, right? So if I think about it geometrically, right? If I go L equals 10, and I think of a a billion-dimensional space, I've got a huge number of hyperplanes. I've got an exponential number of hyperplanes, right, that I'm searching for, right?
This iterator means function of the function.
Yeah.
Yeah, function of the function.
Composite.
Oh,
Position, yeah.
oh, and by the way,
the F functions are nonlinear.
yeah, this is just a simple univariate nonlinear
And what kind
Just-
of nonlinear function is it?
maximum or logistic or than H.
No, but what did Kolmogorov specify for that?
Oh, no, Kolmogorov just proved the theorem, right?
Yeah.
Actually, a couple of people went back and said, what function, Spitzer has an algorithm, given a function, what are the optimum F's to choose, right?
For Kolmogorov, you need to be a differentiable function, I think. Not linear, but differentiable. It doesn't work with the max function, I think.
Yeah, and the other interesting thing is non-differentiability of these inner functions gives you a very wide class. At the moment, the computer science guys, everything's differentiable. It's sort of stupid, right? I'm amazed people haven't done, I think it's Vitushkin in the 60s said, you have non-differentiability in that second, third layer, you get a much wider class of functions much quicker, right? So I'm sure that's a great research topic, right? One other thing I wanted to say was, they call something back propagation. That's the chain rule, right?
Yeah.
Don't you see how everything is renamed, right?
Yeah,
I want the derivative of f of g of x. I call that the chain rule when I grew up.
Yeah.
Now we have to call it backpropagation, right?
Can I
Okay.
ask a question? I think some of the FL, they actually output multivariate.
Oh yeah, sure. So
think
yeah,
the univariate
this
misunderstood.
is still going to be multivariate. So I just apply the univariate to each component of the matrix. Right?
Its output is actually multivariate.
Oh yes, of course, yeah. And actually, if you're doing a data set, right? Suppose I've got a very simple 1,000 dimensions. I just cut dimension in 2 each time, right? I'll do a 10-layer network. I go from 1,000 to 500 to 250. So yes, this each in here is the dimensionality reduction is coming by this semi-affine function, right? Little f is applied to each component.
So this L, my understanding, L is a layer, but at each layer it could have multiple nodes.
Yeah, there's a huge literature on what type of architectures that you can put in here, right? There's at least 50 different architectures. So there's convolutional neural networks, there's LSTM models for time series, there's a whole bunch of structures. So I'm being a little bit, and that's very powerful. Very powerful to know. They'll talk about, okay, I've got a convolutional layer with a logistic output to do classification, with a ReLU layer. So they'll talk in terms of the architectures, the activation functions, and the outputs, right? TensorFlow, let me just step back again, is incredibly powerful, right? YouTube, this will be an order of billions. ImageNet has got, I think, 150 billion parameters to it. So we were talking this morning about scaling up, 10,000, a data set with 10,000. My co-author Vadim would be like, Nick, can't we at least make it 10 million? TensorFlow is very powerful. We talked about it a lump, so any stats model can be written like this, right? So waiting for people to throw things at me, right? You take random forests, I can write it as a deep learning model. Take take a logistic regression, blah, 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 blah. So my point is that if you really wanted to scale up any of these machine learning tools, right? There's a finite number of them, right? We can only do the list, right? Support vector machines, ... right? Every single one I can write up in 3 lines of TensorFlow code. When I first started to do this 5 years ago, I had to code in TensorFlow, which is painful. Now I just have Keras, it calls TensorFlow, and every model I now run is like 5 lines rather than 250. The computational stuff that these Google people have done is so powerful for us stats guys, right? Okay, I've spent a lot of time talking about deep learning, but I just see it coming to stats, right? Okay, I think I'll find one of my examples, maybe the AlphaGo one. People do it for driverless cars. This was for David Rios that wants to know about driverless cars. it solves all these old problems that we used to work on. So there's something called Q-learning if you want to learn about reinforcement learning. If you go to Google, it'll find it for you instantaneously. Let me jump a few, let me do a fun example. Here we go. So, maybe one of my favorite movies, it's only about 1 hour and 20 minutes long, is the AlphaGo movie. So remember, this was Google DeepMind, which is a company inside Google, used deep learning and reinforcement learning to play this very complicated game of Go, right? And let me quickly try and show you how it works, right? So there's two things I need to work out, right? One is something called a value function, and one is called a policy function. So what's the game of Go, right? I have to put these white and black dots, and I have to gain as much ground as possible. At the end of the board will be filled up. I count up how many whites do I have and how many blacks does Noza have, right? Get as much territory as possible, right? That's the Go board. The world champion was a Korean guy called Lee Sedol. He started playing Go at 12 years old. They even play for like $1 million a game. If you go to Korea, you want to bet $1 million at a Go game, there'll be somebody that will beat you easily, right? The Koreans are great at it, the Chinese are great at it. It's their big game. It's been around well before chess. Now, what do I have to do, right? Evaluation means maximize the probability of winning. So I just give the algorithm a goal, probability of winning. Well, so over here, my value function is just going to be the probability of winning. There's some state of the system. The state of the system is just the position of the counters on the board, right? There's 10 to the power 900 possible combinations down here, right? I think chess is like 10 to 154, so it's called the Shannon number. A huge number of possibilities here, that's my state. The value function is the probability of winning. Well, I need to first of all know the value function. Given any possible position of the board, what's the probability of winning? And if you watch the movie, it's only about 1 hour and 20 minutes, right? There's a little graph that goes along. Oh, at the moment, the AlphaGo algorithm thinks it's got a 58% chance of winning.
Well, is that the starting position?
You have to do it for all possible positions on the board, right?
Oh.
10 to the power 900, right?
And then you want to ask what proportion of those would lead you to a win?
Yes. And I would just do Monte Carlo. I'm going to show you 2 little Monte Carlo slides to find out what proportion I would lead to a win, right?
So what have you, in the end, what have you done by just telling me that?
Well, here's what I've done. Move probabilities. I also give you a policy function. I tell you what's my current probability of winning, and I tell you what's my optimum move. If this is the position of the board,
I see.
What's my
How to quickly get to the maximum?
Yes, yes. Now, where does deep learning come in? This function and this function are approximated by deep learning, right? So I've only seen 1 billion games, right? I mean, Lee Sedol must have played, I don't know, 250 million games in his lifetime, right? Well, the computer's played 1 billion.
Okay.
How can a human beat it, right? Impossible.
Yeah.
But 1 billion's only 10 to the 6. There's 10 to the 900 possible board situations. Well, I use Kolmogorov's theorem, essentially interpolation. I fit a deep neural network to the value function and the policy function. So I'm saying deep learning has come to solve all of these, any optimization problem now, or Q learning as you would have called it, or Bellman's equation, now solved by deep learning just because it's so incredibly powerful, right? Another way of thinking about it is this, right? Here's the current Go board. You know, the way you would play chess. Let's think of all possible outcomes, ... all possible branches, right? Well, there's a ridiculous number of branches I'd have to solve, right? So let me make things easier, right? I first of all have to cut the depth, and I first of all have to cut the breadth of the tree, right? So first of all, I'm going to use Monte Carlo to simulate to go forward and find out did I win or not. How do I cut the depth? Well, I use the value function, right? So remember back here, right? I'm never ever going to enumerate all possible branches down the tree, right? So what am I going to, first of all, I'm going to use Monte Carlo. I'm just going to randomly pick branches, go down and see if I win or not. I'm going to use deep learning to approximate my value function, and then I can just cut the depth of the tree, right? If I had a really good value function, I'd only have to go one step ahead, right? I could just instantaneously solve the equation, right? So I cut the depth by the value function, and how do I cut the breadth? I cut the breadth with the policy function. And if you go watch the movie, right, The Korean world champions like, there's no way a computer could beat me. And the computer comes in a laptop, right? They open up the laptop and it starts to play. Now, the humans have no idea what's going on, right? The algorithm has gone through and figured out, okay, if this is the position of the board, here's how I move, right? And all you see as a human is what it thinks the probability is of winning. The computer won 4 games to 1, right? And it was all over Korean television, right? I was amazed that he won 1 game, right? There's this incredible move he played, move 37, if you watch the movie, right?
Yeah.
So he managed to win. Since then, he has won 0 games.
You're talking about Go or chess?
Go. Since then, he has not won 1 game. And of course, what does he do? He just plays the computer now. Same with the chess guys, right? Magnus Carlsen's 2800, 2860 in ELO rating. The best chess algorithm called Stockfish, 3,300. AlphaGo learned it in 4 hours. AlphaGo played Stockfish, won 27 games to 0. The poor guy spent 25 years of his life developing Stockfish. AlphaGo took 4 hours to beat it. And there's actually 10 games on the web that you can watch. You can see how it plays chess. Totally different to humans. None of these opening moves, I mean, I could talk a lot about chess. Very aggressive. So when AlphaGo plays chess, it'll sacrifice a knight instantaneously for like a bishop or for a pawn. It'll sacrifice for positional structure, right? So one of the interesting things about, people are now watching, give it a data set, use deep learning, watch it play chess, and people are like, oh my God, this is just a totally different game from what we used to think it was, right?
So the game should be abolished. What's the point playing?
Oh, it's 0.
I
right?
mean, there's no point playing. The computer is playing the game.
Well, the old joke used to be, Noza, would you like a game of chess? And we ought to shake hands and say draw.
Yeah.
Because 2 of us could do backwards induction. So that was the old joke that. But yes, the humans have, it's not 10 to the minus 100. There is 0 chance that Magnus Carlsen could ever beat AlphaGo at chess. Period.
Is it known that the draw is granted result in chess? I don't.
For the last 6 moves it is, right? If you're down to the last 6 moves of a game, it's known that it's draw chess, right?
Say it again, please.
Sorry, the last 6 moves of a game, it's known to be draw chess. So if you give me any position of the board,
yes,
with 6 moves to go, we know with 100% probability what the answer is. Who's going to?
From the initial position.
Well, in theory.
Yeah. In theory, there is an optimal policy,
Yes.
It's Shapley's result. But my question is whether there is no probability of winning for white and black.
I'm saying known for the last 6 moves, right? But remember how clever AlphaGo is, right? It took 23 million human games. Actually, in the 19th century, the world champion Lask was a mathematician. What are mathematicians good at? Sequential. They're good at just going down a branch, right? 1920s along came Capablanca, Morphy. What were those guys good at? Spatial. They were very good at just looking at the board and saying, okay, I'll sacrifice a piece. The mathematicians couldn't understand because it was too far down there. So the mathematicians fell off. Mathematicians are good at chess, like 2400. Nowhere near as good as Carlsen or Kasparov, right? Carlsen has incredible geographic spatial visualization, right? And when you watch AlphaGo play, it's incredibly spatial. It's not logical like a mathematician, right? It's looking at the whole position of the board. It's incredibly aggressive. It points every single piece of the other person's king because it's trying to maximize the probability of winning. The queen will immediately come to the H rank, and it'll just fire its points. It'll just attack the king. Yes, and it'll sacrifice pieces. So as a kid, you're taught you would never sacrifice a knight. Why would you ever do that, right? Well, it's good enough to control the space, right? So one of the interesting things that people are learning is, why are mathematicians bad at chess? Because they have no spatial knowledge, right? Why is AlphaGo, why is Magnus Carlsen good at chess? They've got very good spatial skills, right? I was walking to the restaurant last night. I had no idea where I was going. I had to follow Simon, hoping Simon was going to get me there, right? I have no spatial knowledge, right? Let me.
5 minutes to go.
Yeah, let me.
Discussion anyway. I would just say keep going.
Let me get near the end. Maybe this will weird you out, but I do some finance problems. And again, for a stats guy, this might weird you out, right? Historical data set, recurrent neural. The way computer science guys write models down is so different from the way that we think about things, right? Because you've got the architectures that go into the deep learner, ... So just to warn you, you won't see equations like yt is equal to ht beta t plus epsilon t. You'll see structures like this, right? All it is just how do I process a historical data set to get some quote unquote optimal weights at the end, right? So I do some finance problems. There's some very interesting things of reinforcement learning in gaming. A lot of these original people that programmed up these things coded up gaming. So I don't know if you've all got kids, you know what Fortnite is and all these types of crazy games. So there's lots of interesting stuff in gaming. I was talking at agent-based modeling, another one of David's topics. A guy called Herb Simon, when we were at CMU together, used to talk a lot about this kind of stuff, and a few years later, it seems as if deep learning is coming to solve these problems. So maybe I'll jump to the end. Oh, shameless Noza.
Yeah.
Totally shameless of me. I wrote a book. You have to go buy it, Noza.
Well, I have it. I bought it already.
You bought it already?
Yeah, I didn't pay anything.
I was going to give you 3 options, right? There's an Italian option of my book for Fabrizio's wife. Did your wife like the book? Did she like it? Didn't really want to admit that, Fabrizio, but I heard a yes down here. Or there's an English version. Actually, I wrote it with a very good friend of mine, James Scott, who works a lot on these things. So if you go to James's website, you see a lot of stuff. Or there's a Swedish version. So apparently, this is artificial intelligence in Swedish. So anyway, let me finish a little early. But yes, I think deep learning is an exciting thing. It's great that SAMC has got I think next week has got a whole deep learning course. But I think it's something our stats guys should get more into. It's maybe a little bit not what we're used to, but very powerful set of tools and techniques. So thank you very much.
A bit of time for questions and discussion.
So you didn't mention anything about Bayesian deep learning. I mean,
yeah, in the all the way back to the beginning, right?
Well,
all of these models are sort of unidentified, right? In a econometrics or in a stats framework, right? All they really want is a prediction rule for an input, right?
But you get no estimation of the uncertainty on the prediction. Just based on
I think the way to do that is just to put uncertainty at the last layer, right? So I think one approach is that would be better than what they currently do is to say, okay, let me put my errors at that output layer. But you're right, we could go errors all the way down. We could try and do sensitivity analysis to the W's. But they're very high dimensional problems, right? So in some sense, yeah, I'm in 2 minds of where the uncertainty quantification will be, right? My sense is just at that top layer, right? You then get standard errors you would underestimate the uncertainty.
But then you can do an MCMC. If you are just considering uncertainty that way, you could do MCMC.
Well, but remember, there's such high dimensional problems, right?
Yeah, but the rest are the standard.
Oh, yes. So uncertainty for me would be at this layer, not for these layers, right? And I think, I spent a lot of my life doing MCMC, right? Stochastic gradient descent, Newton or Robbins-Monroe seems to have killed that old area, right?
No, but it's just for a point from past or another point.
Yeah, but I'm just trying to say, TensorFlow inside MCMC, I think, is another interesting research area. Maybe that's a better way of saying it. But how do you scale TensorFlow or how do you scale MCMC into TensorFlow? I think it's a mistake for us. If you saw the mechanics of TensorFlow, there's at least 50 years of high-level math and computer science went into it, right? It's a very impressive program and it is just, YouTube runs on it. Think of all the videos in the world, right? Actually, they now design chips just for implementing deep learning. So one of the amusing things is the chips are designed to implement the stats model, right? We used to have CPU, that was Intel. Then we had NVIDIA with GPU. NVIDIA's got a set of programs called CUDA, the math libraries. Google has something called a tensor processing unit. A tensor, because like a video is like an image is a 2x2, a video is a tensor, right? So the chips are designed just to implement, So I think that the statistical models have become the computer chips. And there's a big race, but okay, and I need to do everything quickly, right? Ernest wants everything tomorrow. No, Noza wants it.
So by the way, you mentioned Hilbert's 13th problem. That is what Kolmogorov was trying to address. He also addressed the 7th problem, which is probability, I think. Well, the axiomatization of probability is one of Hilbert's problems, and I think it was number 7. But he addressed it. But Arnold's paper essentially says the answer is negative. Namely, Hilbert's problem cannot be solved, or is wrong, or something.
Or Planck arrays, whatever. The 13th problem was Planck arrays conjecture, or one of the Planck array ones.
No, 13th problem was this.
Yeah, but the original person, I think it was one of the Planck array problems.
Well, maybe that's true, but I'm trying to ask you, if you remember, Arnold came up with a negative answer to Hilbert's problem. He said, I've solved the problem, the answer is no. It's in the same series of papers.
I just want to reiterate that a composition is better than in stats we spent all of our lives doing 2-layer additive models, and that was a huge mistake.
What do you mean 2-layer additive models?
Well, whenever you run the old neural networks, you used to just have 2 layers.
Well, forget the neural network. Just talk about regression, which is the only thing.
Projection pursuit regression or principal component regression.
Just classical regression. It's what, 2 layers? Why is it 2 layers? It's only 2.
Yeah, you'd go a sum of Wi, F of X transpose beta.
Yeah, but then you have also the product terms and the interaction terms and all. So you
can make it, yes, but you've still only got a sum of weights times a function, right?
Yes.
Well, this is This is
a composition, which is different from addition.
Very different, yeah.
But a composition could be anything. It includes addition.
Oh, yes. Addition comes in here, right? Then a nonlinear piece, and then a composition piece.
Yes.
And you can, in high dimensions, you're not going to get anywhere with additive structures, right? In high dimensions, you have to have this. And so that's why you have to have backpropagation, because you need to do the derivative of a chain rule, right? So, yeah, I just think that, as I said, my claim is any stats model, random forests, we were talking about it at lunch, right, can be written in TensorFlow, right? I mean, you don't have to do that, but I'm just trying to say that anything that we've done in stats can be computed with, and this can be, Vadim will do 10 million variables before breakfast, right? You won't think about it. The engineers do these way bigger problems, right? And I think that's good news for us, right? It's good news for stats guys that you can run your installed Keras, installed TensorFlow, and
it's bad news for us. It simply says we don't need statistics anymore. That's what it says.
If you're interested in making policy decisions ex ante, which will require you to interpret the parameters out of the model, is it possible to interpret the parameters from that comes out of the deep learning model, like marginal?
Yeah, people are into interpretability for AI. AI interpretability
because
is
a big part of most policy decisions is they have to interpret. Okay, if this variable, if I treat this variable, increase it or decrease it by this amount,
sure.
For public policy reasons, what will be the effect of the outcome? And to me, I'm not sure if deep learning, we can actually make use of deep learning in that frame of research question.
You know what my answer will be. Yes?
Sorry, actually, I think there's one more question. I think you had one question.
Oh, well, a couple of things. I think it's actually possible because the deep learning already gave you a machine. You give data, they can give you all the output. So you can twist your input to give you output. And a lot of like a local approximation by linear method. But you basically can generate a lot of function outputs. You can approximate it very well.
Yeah, I know there are some work in that area, but a lot of people still feel like it's not
Still
really.
not enough.
Yeah, if it's still not as good as okay.
Then maybe we can contribute something.
Yeah.
But another thing I want to mention about the Bayesian is there's actually a lot of Bayesian optimization used for like auto tuning, and very similar to computer model. And so I think that's something like even the
Gaussian processes have become
Yeah.
big again.
yeah. So it's
so-
there's some contribution from the Bayesian side on that.
Oh yes, Gaussian processes is still a big deal. And the policy one, just 5 years ago, I was like, deep learning will never take over in stats, and here I am 5 years later, and like, trust me, it's a tidal wave.
Yeah, I know. It's
A tidal wave is coming,
Really,
and-
it's really good, but I that's one of the things that I'm looking forward in learning. And so if there is something that has already been done that we can do it in that area, I would love to.
Yes, the area is called
get it.
interpretable AI, right?
Interpretable. Okay.
Yes, and there's also the ethics question, because now all these decisions, credit scores are done by deep learning. This is so there's AI and ethics is going to be another huge big field, right?
That's true.
Okay, I think we've got to
Go.
stop.
Great.
Be ethical and stop.
Thank you very much.
Thank you. No.